If you look today where computing is impacting science, you have to consider what is arguably one of the greatest scientific frontiers, and that is understanding how the human brain works. And arguably one of the most exciting tools in this scientific adventure is fMRI, or functional magnetic resonance imaging, that allows us, amazingly, not only to see the structure of the brain, but also its response to visual, auditory, tactile, or to ethical and social situations. And the goal of fMRI is to capture a 3D snapshot of your brain at an instant in time. And the snapshot embodies not just the underlying structure, but also the neural activity in the brain. What is the brain doing and what does it look like? The way this is done is by recording a series of two-dimensional projections, which are then combined into a single 3D volumetric structure. This is very much like reconstructing a 3D model of your body from pictures of your shadow onto different planes. This may seem easy, but 2D projections can be very deceptive, as you can see in this photo of a sculpture. This photo shows that when you view the sculpture from one side, it views as a jumbled mess, but when viewed from another, as shown by the reflection in the mirror, tells a very different story. Of course, sophisticated and powerful computer algorithms perform this 3D reconstruction, yielding spectacular high-resolution images of the brain. Over the past few years, this remarkable technology has revolutionized the fields of psychology, sociology, neuroscience, medicine, and so much more. Now, to me, what's particularly interesting about this technology is that the physics for fMRI has existed for 40 years. So why only recently have we seen an explosion in brain imaging research? Well, in addition to that 10,000-fold increase that I told you about in computing speed, computer cost has dropped by a factor of 10,000 over that same 40-year period. That's roughly the same difference in price between these two properties that you see here. So affordable and fast computing has meant that nearly every major university today is equipped with an fMRI machine, and this is allowing armies of scientists to probe the mysteries of the human brain. In the same way that brain imaging is allowing us to explore the mysteries of the human brain, the Hubble telescope is allowing us to explore the mysteries of the universe. The Hubble telescope is a spectacular feat of science and engineering. And to give you just one example, as the Hubble telescope is orbiting the Earth at 17,500 miles per hour, it must fixate with a stunning degree of accuracy on what it is photographing. Specifically, it cannot deviate by more than the width of a hair as viewed from a mile away. Since its inception, the Hubble telescope has been returning stunning photos of the universe. And it has collected data that has resolved long-standing problems in astronomy and has led to revised and new theories about the universe and its origins. And once again, it was the advances in computing that ultimately led to the success of the Hubble telescope. So this time, in addition to the faster and the less expensive computers, the size of the computers have shrunk dramatically over the past 40 years. In particular, the number of transistors on a typical computer circuit has increased by a factor of 100,000. To give you a sense, that's the same as the difference in area between the entire United States and our tiny little town of Hanover here. So what this has meant is that we can now squeeze more computing power per square inch than was ever imaginable.